So 2.6 is kind of my favorite rule until we get to the next section. So in between product and quotient and implicit, this is my favorite rule. It's called the chain rule. Chain rule. And yeah, I made that graphic all by myself. Chain, look at that. Pretty clever, huh? So in this case, this diagram speaks more to the rule than the image of the chain up above, because of course everyone recognizes that as your favorite Rube Goldberg machine. Yeah, it was packaged by some game company, Parker Brothers, Milton Bradley, I don't remember who, but yeah, it's a mousetrap. And if you remember, you would turn the crank at A, and then A directly affected B. That was it. A affected B directly. But B then had an effect on C, all the way down, blah, blah, blah. You can kind of follow it here. And then at the end, H-I-J-K-L, M, the guy did a backflip into N, which then caused element O to walk down that pole, and then at P, it catches the mouse, right? It was pretty fun, pretty cool. They still make it, so you can maybe do it this weekend if you're interested. But this represents the chain rule because this is a chain reaction, right? A starts a chain reaction that translates all the way to O. And that's what the chain rule kind of is. It's kind of a chain reaction. We can actually write the game version like this. The change in A affects P. So this A down here, hang on, I got to recalibrate my pencil, but the deep independent variables in the denominator. Instead of dy dx, it's dp dA. So if we make some change down here on A, it'll ultimately affect P. But it doesn't affect P directly. Here's how it works. A affects B, B affects C, C affects D, D affects E, so on and so forth all the way down the line until O affects P. And if you multiply those all together, you can kind of see that it works out, because what essentially happens is all of these dudes divide out, right? So it's a chain reaction. You have these independent variables that are affecting one thing and one thing only. And that one thing then starts something else in change, which starts something else changing all the way down the line. So what we're going to be using then is chain reactions for composite functions. So this image of a chain is not far from what we're going to be doing. We're going to be having functions, and then we're going to be chain reacting. They're going to be multiplied by other functions, and the multiplication can be shown by that. And that's going to then be multiplied by another function, multiplied by another function, so on and so forth. And I'll be using parentheses, okay? So if you heard me slip this in, we're going to be talking about composite functions. So here are some of the things we can take the derivative of right now without the chain rule, right? X squared minus 1, sine of x, 3x minus 2, x minus tangent of x. These are the kind of things that we cannot do currently. The first one, the second one, the third one maybe. We can maybe do the third one if we had some time. We could expand it. But what's different about all of those on the right from all of these? This is not just the square root of x, it's the square root of blob. This is not just sine of x, it's sine of blob. This is not just x to the 7th, it's blob to the 7th. And this isn't just tangent of x, it's tangent of blob. So whenever I said the word blob, those are other functions that are nested inside of other functions. These are called composite functions. So guess what the chain rule is going to be used for? The chain rule is going to be used to differentiate, which remember means to find the derivative, composite functions. Chain rule, composite. They both start with C. Chain rule is for composite functions. All right, let's learn the rule. If we let y equal a function of u, and u is a function of g, then y becomes this composite function f of g of x. Okay, so that would look something like this if I had, let's just say, sine of 5x. I would let u equal 5x, substituting that 5x, that composite function, and then I would have y equals sine of u. So you see what I did there? So if I wanted to then find the derivative of y with respect to x, the chain reaction would be, I'll take the derivative of y with respect to u, and then I'll take the derivative of u with respect to x, and I multiply them together. And those du's essentially would divide out, and I'm left with dy dx. So let's see what that would look like. If I want the derivative of y, let's say this is y. I want the derivative of y with respect to x. It's the derivative of y with respect to u. That would be what? Cosine of u times the derivative of u with respect to x, which would be 5. And now all I have to do is substitute back in what was u. U was 5x. And so I get cosine of 5x times 5. So that's what it looks like in Leibniz form. We're not going to really do it that way because it requires what's called u substitution. And you could do these without doing formal u substitution. Okay, in fact, it's just a little bit more work because you got to substitute it out and then substitute it back in. So what we're going to do instead is we're going to think about it in function notation, and we're going to think about it in terms of unpacking boxes with chain reactions. So let's say I want the derivative of f of g of x. So you can see f of g of x, that's a composite function. G is inside of f. So we unpack this function as we approach it from the outside. So the first function we see is f of blob, right? F of blob. So we're going to take the derivative of that first function. So it's f prime of the exact same blob. We just write it down. And now we go inside and we're like, look, there's a g of x in there. So then we multiply by the derivative of that blob, which is g prime of the blob. Now you can even go in one more layer and say, we have another layer, don't we? It's x. And the innermost layer then would be x, and we could even multiply by the derivative of x, which is what? 1. So for composite functions, we don't need the 1 there, of course. You're going to have as many factors in your chain reaction as you do embedded functions. So when you see f of g of x, that's 2 functions, you're going to have 2 derivatives. And if you think about it as unpacking boxes, that's going to be helpful because the big box is f, and so things inside of it have to be smaller. So as you continue to take derivatives, those subsequent derivatives will be smaller in nature, okay? Let me just show you how it works. I think it's probably easier to do that. Let's use the chain rule to take the derivative of this, okay? This is not the square root of x, it's the square root of blob. So what we're going to do is, first of all, rewrite it as if we would do it if it were the square root of x. We'll write it as the blob to the 1/2. Now you work from the outside in. So the first function that you see is blob to the 1/2. So what would be the derivative of blob to the 1/2? Well, by the power rule, it's 1/2 blob to the negative 1/2. If you could say the word blob and write the blob, you don't need to use u substitution. Okay, I think y'all can handle that. And then you go inside and you go times the derivative of the blob. Well, the derivative of x squared minus 1 is 2x. And you're done. So we had the red layer and we had the green layer. We had 2 layers. How many factors do we have? 2 factor groups, right? And the 1/2 is part of the first factor group. And so we're done. We're unpacking boxes. So notice this 2x is smaller than the red piece because it came out of it. It's important to think of unpacking boxes because when we go anti-differentiation, you're going to have to pack things back up into the box. Okay, now after we take the derivative, of course, sometimes we just want to clean it up. So in this case, the 2 and the 1/2 can combine to become just 1, and the x stays in the numerator, and then the blob to the negative 1/2 goes back into the denominator, or goes into the denominator as the square root of x squared minus 1. All right, so that's the chain rule. We unpack boxes. We work from the outside in. However many layers we have is how many factors we'll have. All right, let's try one more, and then we'll set you loose. to try one on your own. This is not sine of x, it's sine of 5x. So anytime your inside function is more than plain old x, whether it's just something as simple as negative x or it's like a huge polynomial, treat it as an inside function, treat it as a chain rule. I put parentheses around it, and I would recommend you do that because adding parentheses helps you see the layers. How many layers do we have? 2. We have the outer function, sine of blob, and the inside function, 5x, which is the blob. So we'll have 2 factors. We work from the outside in. What's the derivative of sine of blob? Cosine of the same blob. You don't want to take the derivative of both pieces at the same time. So don't call that cosine of 5. Don't do that. It's cosine of the blob. And then times, then you go to the inside, and you're like, oh, times the derivative of 5x, which is 5. And, of course, if you simplify that, you can actually start unpacking your boxes on the left side instead of the right side if you wanted, and then you wouldn't have to rewrite it at the end. Got it? Composite functions. Unpacking boxes. Go ahead and try this chap on your own. That's it. That was it. You got blob to the 7th power. It's not just x to the 7th. You got a function of x. It's linear. So we work from the outside in. Blob to the 7th is 7 blob to the 6th. Now, if you kind of pay attention to how I do this every time, this is how I do it. I don't really write down the blob at first. I just do 7 parentheses to the 6, and then I come back and write the blob. It's just how I do it. You'll see later on that if you start to write it from left to right, that exponent up there of 6, you can tend to leave it off, believe it or not. Because you know you're doing the power rule, but then you're focusing on writing the terms down, and then by the time you get to the end, you forget to write the 6. So I always do that first. You're less likely to leave an open space like that, right? If you concentrate on 7 blob to the 6, you're less likely to say, oh, that looks good, right? Whereas if you're missing a 6, you're not necessarily going to notice it, right? So that's why I do it that way. All right, so there's the outside derivative, and then times the derivative of the inside function. 3x minus 2 generates a 3. So that's it. That's the derivative. If you then want to combine it, 7 times 3 is 21. And you're done with the derivative. So the guy who doesn't know the chain rule, he's still foiling it out. Loser, right, to the 7th power. It's going to take a while. That's probably the same guy who thinks that the expansion is just this, right? It's probably the same guy. In fact, he probably doesn't even put parentheses around 3x. He probably just thinks that's the expansion. What are you doing in this class, whoever you are? That's a fictitious person, so don't be offended. All right. ABC, what comes next? D. Yeah, he's over here. There, you do it. Go. There's a lot of letters in this section. You go all the way through I. If you feel I'm holding you back, just jet ahead. We'll catch up with you Monday. All the rules that we've already had in the past, they still apply. Power rule, sum and difference rule, trig rules. You got two terms. Do either one of them need to be rewritten? I don't think so. So you don't really need to write the ddx again. But the first term is pretty simple. It's x. The second term, that's the one that has the composite function, because it's not just tangent of x, it's tangent of x squared. So that's where I would add parentheses around the x squared. And I would just add them right there in the beginning. So now we'll take the derivative of the first term. That's just 1. And then minus tangent of blob. What's the derivative of tangent of blob? Yeah, secant squared of the blob. Now notice what I did there. I left a little space between the negative and the secant squared of x squared. Because after you do the chain rule enough, you'll realize that you can unpack boxes on the left. Times the derivative of x squared, which is 2x. And that keeps you from having to rewrite it. Because if you unpack the 2x on the right, you'd probably write another line just to bring it to the front of that term. So that's it. That's the derivative. 2 layers in the second term, 2 factors in the second term. All right, E. Wait, let's look at E together. Do you need the chain rule for E? Or is it even a chain rule? How did he get in the chain rule section? That looks like a quotient, doesn't it? That looks like a Hody High fella. Could you do Hody High on him? Sure. Yeah. What would D high be? 0, right? You could do that. If you ever have a constant over a function of x, I'll use the constant as c, it's going to be a little bit faster, believe it or not, especially for higher order derivatives, to bring it to the top and say it's to the negative first power, and then use the chain rule. It doesn't have to be 1, it could be any constant. It's a little bit faster, especially if we take higher order derivatives. So you could certainly use the Hody High rule here, but I'm going to go ahead and just bring it to the top and say it's to the negative first power. And now because I have the quantity to the negative power, there's no way to expand that. It's not just x to the negative first, it's x plus 1. So that's a composite function. So this is the chain rule. So the outside function is blob to the negative first. By the power rule, that's negative 1 times blob to the negative second power. And then times the chain rule, the derivative of x plus 1, which is what? It's just 1. So if you needed to take another derivative, second derivative, notice it's ready to go again. If not, you can clean it up just as easily. It's negative 1 over x plus 1 squared. And you can verify you get the same answer as that as using the Hody High rule. Now, if that were another function of x in the top, x over x plus 1, then the Hody High rule is probably the way to go. Unless you do long division or something like that first. Okay, letter F. Sine squared of 3x. How many layers do you see there? Kind of hard to see layers here because this is by nature a condensed version of a function. It's good for traveling with, not really good for using. So let's go ahead and write it in expanded form. We're actually squaring the sine function, so it's sine squared, and then we have sine of, and then we have 3x. How many layers do you see there? There's 3 layers. So if you ever have anything written in condensed notation, write it in expanded notation, and again, add grouping symbols around inside functions. You have the squared layer in blue, you have the sine layer next in purple, and then you have the linear 3x layer in green. So we just work from the outside in. The derivative of blob squared by the power rule is 2 blob to the first. And the blob is just sine of 3x. Now we go in 1 layer, and we're always referring back to the original. Okay? The derivative of the next layer of sine is cosine of the blob. And then we look up for the last layer, which is 3x, and its derivative is 3. So there's your answer. Derivative is over. Derivative only lasts 1 line. Now there's a couple of ways we can simplify this. The easiest way to simplify it is just to bring the 2 and 3 together and call it 6 sine of 3x cosine of 3x. That works. But there's another way. If you think about these guys right here, and this would, of course, be maybe on a multiple choice question or even on a free response. If we were trying to solve an equation or something, we could do something with that. What would that be equal to? Do y'all remember? 3 sine? Well, let me jog your memory. Sine of 2x is 2 sine of 1x cosine of 1x. So if you ever see 2 sine times sine, it's going to be a double angle for sine. Well, if this angle here is x, and on the left side it's twice whatever x is, since we have a 3x there, if I use that identity, it's going to turn into sine of what? 6x. Good. And then what about the 3? He's still there. So that's another way to do it. You can call it 3 sine of 6x from the double angle identity. Okay, just we'll be kind of making you aware of those double angles on and off throughout the year. The cosine of 2x, just so you know, is the one that looks like Papa Pig. Cosine squared of x minus sine squared of x. All right, I think we have time for maybe one more. Let's finish strong with this ugly one. You walk up to the problem, and you're like, what's up, problem? X secant? What operation is between there? Multiplication. That's x times secant of blob. So what rule do we use out of the box here? Product rule. Excellent. The product rule first. So let's do the product rule. 2 factors, 2 terms. The derivative of x is 1. The second one goes along for the ride. Plus, now the x goes along for the ride, and it's time to take the derivative of the second factor. Well, it looks like the second factor is a composite function with 2 layers, right? See that? So working from the outside in, the derivative of secant of blob is what? Secant blob? Tangent blob, right? Oh boy. It's not just secant x tangent x. It's secant blob tangent blob. And we got some blobbiness going on there. All right. And then this is why we always refer back to the original problem and not what we're creating. Because if you look back now, you might see tangent. You don't keep taking the derivative of what you created. You only take the derivative of the original problem. So now we're going to multiply by the derivative of x squared plus x plus 1, which is 2x plus 1. And if you finish like that, is that finishing strong? Uh-oh. What happened? What am I lacking there? If I leave it like that, it looks like it's x times secant blob tangent blob times 2x, pause, plus another constant, 1. Yeah, parentheses. Yep. Better to have them and not need them than to need them and not have them. Especially important when you have multiple terms and multiple factors. Yeah, better to have them and not need them than need them and not have them. So in this case, we do need them. Now, if you wanted to simplify it, there's 2 terms. You could possibly factor out a secant of blob if you wanted to, but that's not the purpose of this exercise, right? So all the rules that we had in the past, quotient, product, power, trig, they can all now be intermingled with this new rule for composite functions called the chain rule. Okay, so there it is. Chain reaction, something times something. And think of those little chains up there as being parentheses, right? And you're not going to not have them when you need them. You might have them when you don't, but that's fine. Okay, we'll stop right there. Have a super duper splendid, awesome, wonderful weekend. And don't feel mad that Seguin has not been in school the last 2 days. Don't let that bother you, okay? Because we're just learning more than they are. One day, Thursday was teacher work day all day long, and then today was their fair day, the Guadalupe County Fair. So they did it so that they get 2 days off instead of one.